Hello, honors friends. Today we're going to talk about the first section in chapter 2, and actually the first couple sections of chapter 2. First one is 2.1, which is properties, and I gave you these notes. You should have the notes in front of you and a pencil so you can take notes along with me as I explain some of the terminology. We're going to talk a little bit about some English words and then relate them to how they are in mathematics. So I want to talk about what the word commute and what the word associate mean in English. When I think of commute, I think of my commute from work to home. I change places. To commute means to change places. I go from work to home and from home to work. When I think of the word associate in English, I think of grouping. If I associate with some people, I'm grouped with them. If I belong to an association for teachers, I belong to a group of teachers, and we all have a common goal. Well, these words have similar meanings in math. To commute means to change places, change the order. To associate means to group your terms. So let me show you what that looks like mathematically. So the commutative, note this is not commutative, this is commutative property of addition and multiplication says it doesn't really matter what order your addition comes in or your multiplication comes in, your answer is the same. So, for instance, 3 plus 4 is the same thing as 4 plus 3. It doesn't matter which term we list first. And conversely, on multiplication, 3 times 4 is the same thing as 4 times 3. Moving on to the next page, we're going to talk about the associative property, again, of addition and multiplication. If you have 3 numbers that you are adding together, the associative property says it doesn't matter which 2 you start with. You can group any 2 of them together to start. So if we say, okay, I'm going to choose to add 3 plus 4 and then 5 and get 12, my friend on the other side of the equal sign might say, well, you know, I'm going to add the 4 and 5 first and get 9, then add the 3 and still get 12. And we could have a third possibility of saying, well, I'm going to add the 3 and the 5 first and get 8 and 4 and make 12. Any association of these numbers will yield the same answer. Of course, these only work for addition and multiplication. When you get into subtraction and division, you have a whole nother story. Let's talk about the identity properties of addition and multiplication. When I think of identity, I think of who I am, myself. In mathematics, it means what can you add or subtract or multiply or divide to your original number and still have the result be identical, identity, to the original number. So for addition and subtraction, our identity element or number is 0. We can add or we can subtract 0 from any number and still have the number we started with. Of course, the identity element can't be 0 for multiplication and division, but it's 1. So 3 times 1 or 3 divided by 1 still end up with the original identical element that we started with 3. So here's the algebraic representation of the identity property of addition, where we add 0 to a, remembering that a means any number. Any number plus 0 is itself. And the identity property of multiplication, any number times 1 is itself. All right, we've got just a few examples to run through. You don't have examples 5, 6, and 6 on your notes. If you will write them down, we'll start with them and then go back up to the algebraic ones. So I look on either side of the equal sign. The very first thing I look at is my order the same? I have a 5, a 4, and a 9. I have a 5, a 4, and a 9. The order is the same. Because the order is the same, this is not the commutative property. I also look for grouping symbols. Here I have the parentheses around the 4 and the 5, and here I have parentheses around the 4 and the 9. Those are two different ways to associate these numbers together. So this happens to be the associative property of addition. If we look at the next example, again, I ask myself, is the order the same, like it was in number 5? I have the 6 times 7 here, and then adding 3. Over here, I have the 3 first, and adding the 6 times 7 on the back end. My order did change. So when we think of the word commutative, my order changed. So this is the commutative property of, again, it's of addition. Now let's go back up and take a quick look at the algebraic expressions, equations up here. We ask ourselves, what changed? Did the order change or did the grouping change? Well, my grouping is B plus C. Over here it's B plus C. My grouping did not change, but the order changed. This side of the equal sign, the A comes first. This side of the equal sign, the B plus C comes first. This is a commutative, I'm going to abbreviate, property of multiplication because that's the primary thing we're doing in this equation. The second one, did the order change or did the grouping change? Don't be tricked on this one. Even though there's parentheses, grouping symbols, what they grouped did not change. The order changed. C comes first on this side and second on this side. This is the commutative property, but it's of addition. This one, let's see. What changes? It looks like the order. Again, the C comes second and the C comes first. Commutative property of addition. Now, I haven't used any associative properties. I wonder if I do here. Let's see. This one looks complicated. But again, this is my first term on this side of the equal sign. On this side of the equal sign, what changed? I don't have the same grouping. Over here, I grouped C times A plus B, adding D. And over here, I grouped the D and the E to start the process with addition. So this indeed is the associative property, and it's of addition. So we'll review some more of these in class, but this will at least get you started on the commutative property. And I am going to end this video and tack on the unit analysis piece of it coming up next. So let's get your second note sheet, and I will get it up on the smartboard, and off we'll go. Let's see. I need unit analysis. And here we go. So we're going to do a lot of unit analysis. You're going to do this in science. I think you're working on conversions in science right now. So this is kind of neat that Mr. Rock and I are doing this around the same time. Most of our conversion, most of it, will be customary units, but we do some metric and some dollars, money conversions as well. The way that I do conversions with you guys is by units. And I think in science you're looking at the units as well. And what we are going to look for when we do our unit conversions is we are going to look for a fraction that makes the number 1. We said in chapter 2.1 that the multiplicative identity, the number that we can multiply anything by and maintain his identity, is 1. But there are many, many ways to write 1. Here I've listed 3 different ways to write the number 1. Anything divided by himself is 1. So here's one representation of the number 1 using division. Here's another one. And here is another one, because 3 feet is the same thing as 1 yard. So these actually equal the number 1, just like the first 2 examples. So we're going to use these conversions with units to help us get a conversion problem, get a conversion done to a different unit based on being able to use a conversion factor that actually equals out to 1. So here, I'm going through an example with you kind of slowly, and then we'll work some in class. This Steel Dragon is the world's longest roller coaster. Probably not anymore, but anyway, it's pretty long. So it's 2711 yards, 2,711. How long is the roller coaster in feet? So the first thing we're going to do is write down what we know with the units. Do not leave the units out. We have 2,711 yards over 1 roller coaster. This 2,711 yards equals 1 roller coaster. The next thing we're going to do is look for a conversion factor that has that's equivalent to 1 and has yards in the denominator, because our yards in the original problem are in the numerator. If we can find a conversion factor with yards in the denominator, left off my S, we can cancel out these yards and end up with just what we want, or the feet on top. So I know there are 3 feet in 1 yard, and I'm going to write it with the feet on top, so my yards will be in the denominator to nicely cancel out with the yards in the numerator. So I now have a multiplication problem. I can cancel out my yards and yards. I can multiply straight across, and now I end up with 833 feet. That's the unit that's left, which is what I wanted. Example number 2, African elephant. He's the largest living land animal. He weighs a hefty 6 tons. What's the weight of the elephant in pounds? First step, write down your given measurement. Write down what you know with the units. 6 tons over 1 elephant. Now we need to think of a conversion factor that's got tons in the denominator. It's going to be down here. So ultimately these guys can cancel. And we want pounds to be in the numerator. So if we think of a conversion factor, 2,000 pounds is the same as 1 ton. So the next step would look like this. The tons would cancel. 6 times 2,000 gives you 12,000 pounds for 1 elephant. Example number 3. The Boston Marathon is 26.2 miles long. It's run the 3rd Monday in April. How long is the marathon in feet? First step, write down our given measurement with the units. 26.2 miles over 1 marathon. Think of a conversion factor that's got miles in the denominator and feet in the numerator. So if you don't remember how many feet in a mile, this might be something you look in the back of the book for. 5,280 feet in 1 mile. So that's now what you're going to multiply by. Your miles cancel. Your 26.2 times 5,280 equals a ginormous amount of feet in 1 marathon. Looks like I've got one more example. Use unit analysis to convert 3 years to hours. So we have 3 years over 1, whatever, we don't really have a unit there. We need a conversion factor that's got years in the bottom. Now what we know is there are 365 days in 1 year. That's where we're going to start. It's not going to end up, let's see if I got to move this guy over, find my page. There we go. Put him back over. So we have 3 years times 365 days in 1 year. The years cancel. That's good. Now I've got 1,095 days over my 1 still. However, I don't want it in days, I want hours. So we need to find another conversion factor that's got days in the denominator and hours, hopefully, in the numerator. So here's the conversion factor. We're at 1095 days over 1 times 24 hours in 1 day. Cancel your days, and you end up with a large number of hours for the years, 3 years. Lots and lots. So if you need to look back over this video again, please do. We're going to do a bunch of these conversions. They get more complicated, but it's important that you understand at least the basics to begin with. Thank you, and see you tomorrow.